Hi, this is Nick Veach. I've been reading a lot of Randall Carlson lately, and I've been particularly fascinated by his discussion of the Carolina-based meteor impacts. Frankly, I'd like to learn a hell of a lot more about this because it seems to be of a very kind of pressing danger that I was heretofore completely unaware of. The Carolina-based meteor impacts are these things here. This is a LiDAR, kind of ground penetrating radar. And this is just like about, I don't know, about 12 miles across from left to right. This is in Robeson County, North Carolina, and these are all like meteor impacts. And these are apparently the oldest age, as I recall from Randall Carlson, was he said about 100,000 years, and the youngest would be 20,000 years. But if you do a little bit of extrapolation, if you extrapolate from the number of these impacts up and down the seaboard, and you extrapolate across the rest of the United States, you start to rack up a huge number of impacts. Even at the best case scenario, which would be that these impacts occurred over the last 100,000 years. And this would help explain a lot of what's been going on. I mean, the massive extinction, the way in which animals were killed off, even the way in which animals were seen to apparently they were crushed by this oppressive force, bones broken, animals mangled in a manner which obviously seems to have had nothing to do with other wild animals or to do with predation by human beings either. And I think a lot of this stuff actually can be attributed to precisely this phenomenon that you're looking at right now, the Carolina-based meteor impacts. So let's get into this and take a look. And it's not just somebody like myself or Randall Carlson, etc., who's concerned about these kinds of things. It's also people like Elon Musk, as far as I can tell. In recent years, there's been a bunch of stories, featuring billionaires saying that we need to get off this planet for one reason or another. And just advocating that we go out into space and populate the moon, Mars, etc. Here's Elon Musk talking about it. What's interesting, in part, and the reason I'm showing you this is because for his explanation, he goes to almost say the word cataclysm. He pronounces "ka," and then he stops, goes and he goes back and says, "No, it's because I'm afraid of a third world war," just kind of amusing. Check it out first, and then I'll try to explain it later on.
If you know that there's likely to be, we don't know, but there's likely to be another dark ages, which it seems, my guess is there probably will be at some point. I'm not predicting that we're about to enter dark ages, but that there's some probability that we will, particularly if there's a third world war. Then we want to make sure that there's.
So that's the pretext, whatever else that he's throwing out. There's going to be a third world war. But you'll see when he's thinking, if he forgets about this pretext, he tries to say something entirely different. I think anyway.
Enough of a seed of human civilization somewhere else to bring civilization back, and perhaps shorten the length of the dark ages. I think that's why it's important to get a self-sustaining base, ideally on Mars, because Mars.
Here it comes.
Mars is far enough away from Earth
what's a cut?
Sustaining base, ideally on Mars, because Mars is far enough away from Earth that
a cataclysm,
a war on Earth, the Mars base might survive.
There you go, and he changes it to war. I presume he's doing that just because it's easier to pitch that to the public, and the public can understand what a war is, the concerns there, and then and then the worries that if there was a nuclear war, that everybody would be wiped out, that kind of a thing. But I think his real concern is cataclysm, which is why he went to go and then he changed up. When it comes to cataclysms, there's basically a couple of kinds. One is your coronal mass ejection, which is what you're going to see here. I'm sure you're already familiar with it. Kaboom, right there. And the second kind results in this kind of crater. So when you have like a really heavy kind of meteor, which is made from nickel or iron, something like this, and it results in this, it makes it all the way down through the air and hits really super hard, coming down at multiple miles per second. And it hits with the impact of, let's say, I don't know, 10 megatons, something along that nature, basically. It's huge. However, what we're going to be talking about today, and I'll try to keep it short, is this particular kind of impact, which is totally different, whereby the meteor doesn't make it all the way down to the ground, but instead it explodes in the air. You probably remember this from the Russian meteor from 2013, which exploded up, I don't know, about 5 miles or so up in the atmosphere. This baby right here.
Нихуя себе,
Kabloom!
это что такое? О, нихуя метеорит, блядь.
So then how do we get the formation of these? Well, here's how it happens.
Я сейчас подойду, подожди.
Here it comes. That's how it happens. And again, well, that blast happened, fortunately, really high up in the atmosphere. However, if you have a lower level event, you get something which is like the Tunguska Event, which is from 1908. And this was a large explosion that occurred in blah 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 in Russia on the morning of June 30th. The explosion over the sparsely populated eastern Siberian taiga flattened 2,000 square kilometers. That's 770 square miles of forest. Okay. So it's contributed to an airburst of meteors, chondrite meteor basically. What you have is a combination of rock and frozen methane and water. And when this thing comes blasting through the atmosphere, you have a combination of super high speed, super high heat, plus you have the oxidation of the methane, which just gives you this enormous blast. If it's a sizable meteor, let's say of 150 feet or something like that in diameter, which apparently is what caused the Tunguska event. In which case you have this monstrous explosion. It's like a thermonuclear bomb, 10 megatons, that kind of scale, which is how it could flatten 770 square miles. Okay, which is an enormous area, resulting in it's a terrible picture. Sorry. And okay, here's a better picture. So it just totally flattens the forest. Okay, 770 square miles of this. So what did the impact crater look like? Looks like that. Look familiar? You seen that before? Does it look anything like this? What do you think? That? Same, 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 same. Okay. And that. So in other words, what we're looking at, I presume, is in Russia you had one blast wiped out 770 square miles and basically would have killed most of what was in there of any size. Now look at the density of these impacts here on the North American seaboard. And now this apparently again is racked up over, let's say, 100,000 years. That's the best case scenario. Worst case scenario is 20,000 years. Apparently, according to Randall Carlson, there's 500,000 of these on the eastern seaboard. 500,000. Okay. Okay, let me just slightly correct what I was saying before. According to the Wikipedia here, the airburst, the estimate for the amount of energy was 10 to 15 megatons, so it's larger, even up to 30 megatons. The size of the rock or meter itself is a bit bigger than I was saying. It's 60 to 190 meters, so it's 200 to 620 feet, depending upon whether the body was a comet or a denser asteroid. Again, just to push the point home, it is estimated that the Tunguska explosion knocked down some 80 million trees, and that the shock wave from the blast would have measured 5.0 on the Richter scale. An explosion of this magnitude would be capable of destroying a large metropolitan area, right? And at the same time, that is all that was left behind in terms of crater. Again, here's one of these impact craters in America. Without LiDAR, it's not that obvious. But you can see it here. You can see maybe there's a second one there. There's a third one there. I don't know if that's one or not. At the ground level, it just looks like this. It just looks like a, like a pond, basically. But with LiDAR, you can see what's really going on, right? And again, these are like what, 0, 1, it's like 2, 3. The biggest would be, let's say, a bit more than a mile. And as you can see, this is significantly, less than a mile. So we're talking serious, serious, serious damage here. Okay, as I mentioned, there's 500,000 of them are present in the classic area of what's known as the Atlantic coastal plain. Here's the Atlantic coastal plain. See if this will, yeah, there we go. This will size up for us. Okay. So let's just do back of the napkin extrapolation. What percentage is that of the continental United States? I would say that this is no more than 10%. Probably less than that. Probably less than 10% of the continental United States. So if we just do the math, let's just keep it simple. Let's multiply. 10 times 500,000 is 5 million. What I'm presuming is that these impacts are not limited because they're out there up and down the entirety of this coastal plain, and the reason that we find them there is simply because of the nature of the soil of the land. It's just much softer. The surface doesn't feature bedrock. It's alluvial soils and sand and loam and all the rest of that. So the impressions remain. Whereas in the rest of the continental United States, if these impacts were made, there'd be very little evidence, if any of them at all. So again, we're working with 5 million of these impacts. Let's take the best case scenario, which is 100,000 years. That's an average of 50 a year. That's 50 of these Tunguska events a year on average. 50. Okay. Which kind of makes sense when you look at how thick this is. I mean, that's just crazy. I mean, that's like a lot of these are Tunguska size events. Jesus Christ. Now, presumably they didn't all come down in a nice, neat average. Presumably they came down, let's say, you'd have a spree, let's say once every 10 years or 20 years or 50 or 100, whatever else. But you know, if you multiply it, if it's once every 100 years, that's 100 times 50. That's all of a sudden America gets, what, 5,000 of these? It's 5,000 thermonuclear bombs. Kablam. Etc. Here's a reconstruction of Greenland temperatures from the University of California at Riverside. I think it's Riverside. Yeah, Riverside. This is 100,000 years ago, 80,000 years ago, all the way down to the present. Here's how stable temperatures have been when we've been in the modern era, basically, since the end of the last ice age. And here's what temperatures have been like before. It's absolutely insane. Massive, massive, massive changes. So, what Carlson is saying is one of the reasons you want to account for this is this massive impacts, just this like thermonuclear power or scale explosions, just these massive kind of rainstorms of comets coming in, or microcomets or parcels of comets, whatever else, and just raining down on the planet Earth and leaving these scars. I mean, and again, look at the. It's just amazing. Look at the concentration. I mean, it's just everywhere. It's just it's just pockmarked with this stuff. I just think that's just crazy. So imagine something like I can't reproduce it here because there's nothing on video, but this is kind of a vague, the most vague of approximations. But imagine 100 or 1,000 of these things coming down in the space of a few months or something, or whatever. Imagine that thing in the sky, but imagine it coming down much lower and just blasting everything to smithereens, and not just one of them, but them coming down in potentially dozens or even hundreds at a time. And that would go far to explaining stuff like this. Kaboom! These crazy fluctuations. It's not the only factor. There are other things as well. There's dust from when our planet travels through comet trails. There's all kinds of other factors as well, but a major one, I'm sure, and one which would really have a very serious impact upon our own ability to survive as a species, would be these impacts. Sorry, these impacts. Anyway, I guess it helps to see a few real shots, not just LiDAR, because LiDAR looks like some kind of pseudo-science-y extrapolation from the real thing. But, I mean, it's just, they're everywhere. Boom, 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 boom. I mean, look at this stuff. It's just nuts. More LiDAR. More LiDAR. More LiDAR. I mean, it's just... And there you go. Gazoom. Oh, I guess I found some out here too. Anyway, okay, I'll wrap it up with this. In my next video, I'll deal with how I think this you can see evidence of this in terms of the wildlife extinction, direct evidence of this. Some of which Randall didn't get into. I find it hard to imagine he hasn't thought of this himself. I'm sure he has. He's thought of all these things long before we have. But nevertheless, he didn't mention this video, so I'll deal with it myself. Anyway, all right, thanks for listening, guys. Nick, see you next time. Bye-bye.